Hi everybody, this is your video notes on function summary. This is going to cover the main parent functions that you should be familiar with by now. And these video notes that you're going to take are going to cover 4 to 5 different types. It's going to preview the 5th type, just so you know. I realize you don't have this taped in your notes, but there's not too much stuff to write. So just fill out all the notes that are on the video here, and you'll be referring to these video notes in class whenever we do the different matching and function summaries once we finish rational functions. So let's start with linear. We'll very briefly go through this one since you've seen it so much. Linear is a first degree. Now some of you are forgetting what the word degree means. Degree means the largest exponent. And it has a constant rate of change whose graph is a line. And there were 3 possible forms here. The names you don't want to forget. I realize we haven't been saying their names a lot, but you shouldn't be letting these slip away from you here. We have slope-intercept, we have point-slope form, and the last one that you were probably ever introduced to was standard form. Now slope-intercept form, when you do mx plus b, we have our slope for m, and for b we have our y-intercept. This was the only form that gave us the slope and the y-intercept directly. Point-slope form was y minus y1 equals mx minus x1. You could do y2 minus y1 and x2 minus x1. Either one's fine. The last one that you worked with was standard form. Standard form we saw a lot with linear programming, whenever you had the constraints and you would graph them. And the way you graph them is we graphed using x and y intercepts. So at the x-intercept, you let y equal 0. For the y-intercept, you let x be 0. That's how we plotted those. Now, whenever you graph these, again, there's infinitely many possibilities, but a line like that would have a positive slope. Jot down the 4 different types of slopes: positive, negative, undefined, and 0. Another thing to keep in mind is whenever you look at a table that's linear, because what you're going to be doing is getting various tables, and you're going to have to be able to determine what function type it is. You'll just look at the rates of change. So this one here is obviously a +2. Because there's a constant rate of change, not only is it linear, but you can actually say that the slope is 2. So that's the linear functions here. Let's move on to the next type that you did, and that's quadratic. So write down anything you didn't get for linear yet, and let's do the quadratic functions. So a quadratic function is a second degree function. So second degree function, and it's going to have constant second differences. Now the graph, whenever you sketch it, will always end up being a parabola no matter what. And remember the 3 forms we did here. We had a standard form. Then we also had a vertex form and an intercept form. And we learned them in that order this year. You worked with all 3 types. Standard, remember we practiced looking at the 3 cases or the 3 types and what their advantages and disadvantages were. Standard, you can't see the x-intercepts easily, but you have the y-intercept. Vertex, you obviously have the vertex right in front of you, but it wasn't super accurate to graph. That's okay. And then intercept form was nice because it gave you the x-intercepts, and you could easily get the vertex because it was halfway in between it. But you didn't necessarily see the y-intercept right in front of you. And the vertex, whenever you do it in vertex form, is HK. Whenever you graph these, there are 2 things that can happen. Upward shaping parabola if a is greater than 0, or a downward shaping parabola if a is less than 0. Just remember, a not only tells you if it's upward or downward facing, it also tells you if the parabola itself is narrower or wider. And that depends on if a is greater than 1 or less than 1. Now, whenever we look at a table, you know a table is going to be quadratic when the first differences are not constant, but then when you look at the differences of the differences, you see that those are constant. That means you have a quadratic table or a quadratic relationship between your outputs. Next one that we're going to look at, make sure that is all written down, is polynomial, which is just the generalization of what we've been talking about. Linears, quadratics, cubics, quartics, all of those are polynomials. A polynomial is just a smooth a smooth and continuous function in the form f of x equals a x to the n plus b x to the n minus 1 plus c x to the n minus 2 plus dot dot dot, and then there's some constant at the end, k or d or m, whatever you want to call it. Remember, the standard way to write it means your exponents go in decreasing order all the way down to the constant at the end. And your constant could be 0. It just means there wouldn't be a number down there. And whenever we sketch polynomials, our end behavior was huge. The end behavior was determined by a out front. The highest exponent, or the degree, remember, don't forget what that word means, is n. So the exponent that is the largest. Keep in mind, now that you've done enough polynomials in your time, we didn't specifically say this, but let's say I have a polynomial of degree 4. So 4 will be n. I can have up to 4 zeros. And if there are 4 zeros, you need to consider turning points sometimes. So if I'm going to connect my 4 zeros, that'd be 1, 2, 3, 4. You want to think about how many turning points you can have. A turning point just means exactly what you think it would mean. The function actually turns around. So there, there, and there. Whatever the degree is, the number of turning points will always be 1 less than the degree. Now, the reason I said at most n minus 1 turning points is because what if I were to have, again, n being 4, but my graph looks something like this? That could be a 4th degree, but I only have 1 turning point. So what you need to consider is your imaginary solutions. So if you have imaginary solutions, that will affect the number of turning points and the number of zeros, but you can have at most n minus 1 for your turning points. All right, the next one that we talked about was a rational function. Now, a rational function is a function that is the quotient, meaning you divide, of 2 polynomials. And I know you've seen this before, but this is just a recap. And it's going to be in the form p of x over q of x, where p and q are polynomials. So p of x and q of x are polynomials. Keep in mind that q of x cannot be 0 because that would mean you would be dividing by 0. Now this function is not continuous. It usually isn't continuous. Remember, sometimes we had those rational functions that did something like that, and there was no vertical asymptote. So it usually is not continuous. It'll have domain restrictions. The name of the graph is a hyperbola with imaginary dotted asymptotes. That was a big vocab word for this unit. To represent domain restrictions, which would be vertical asymptotes, and end behavior, which is horizontal asymptotes. Now the values where the function is not defined, those are, again, either going to generate, I should clarify, vertical asymptotes, or if you have a common factor on the top and bottom that cancel, it could be a hole. Now whenever you graph these things, a very typical graph that you would see is going to have 1 vertical asymptote and 1 horizontal asymptote. And again, when we did this by hand, you can really have many different things. The asymptotes are, you're just going to approach it on each side, getting infinitely close. And you never cross a vertical asymptote, remember. Now, if you have a table, the way that you're going to know that a table is a vertical asymptote is usually you will see an error. Not always, because if you have a rational function that looks something like over here, there was no errors. But it's still rational, technically. Often than not, you're going to see error in the table, and that's a dead giveaway that it's a rational function, because only rational functions would have an error and a domain restriction there. Now, one thing that I want you to write down in your notes is this visual, and this visual is going to show you the hierarchy of functions. The general type of function we have is a rational function. Within rational functions, we have polynomials, because remember, a rational function is made up of 2 polynomials. In polynomials, you have many, many different kinds of functions. You have linear, you have quadratic, you could even put cubic in there, quartic, constants, anything like that. Just realize that rational is the most general, and something like a linear or quadratic is a more specific one. What we're going to be doing next, just so you know, is an exponential. An exponential is a function that shoots up like this. You saw that once in class so far, and we'll talk all about the form of those next. So get these notes down so you can refer to them in class, and have a great rest of your break. Bye.